Welcome to today's Explainer. I've always kind of looked at algebra as this abstract jumble of floating letters and numbers. It can feel really disconnected, right? But it turns out we can actually pull it right out of the textbook and into the physical, three-dimensional world. We're going to see visually and structurally the undeniable geometry behind math together. Algebraic identities aren't just arbitrary rules someone made up to make tests harder. They are literally the geometric DNA of numbers.
Okay, let's dive into this. Here is our roadmap for today. 1. The magic of math patterns. 2. Visualizing algebraic identities. 3. Factoring with algebra tiles. 4. Master list of identities. 5. Applying identities to problems. And finally, 6. Viewer quiz and practice.
Section 1. The magic of math patterns. So, let's kick things off with a pretty wild math puzzle. Think of 3 consecutive square numbers. Let's just use 1, 4, and 9 for now. Now, I want you to follow this specific rule. Add the smallest and largest squares together. So that's 1 plus 9. Then, subtract exactly twice the middle square from that sum. Take a second, do the mental math. Did you get 2? Well, 1 plus 9 is 10, minus 2 times 4, which is 8, leaves you with 2. Now, what if we tried it with much bigger squares? Let's say 25, 36, and 49. 25 plus 49 is 74. Subtract twice 36, which is 72, and you get 74 minus 72, which is exactly 2. I mean, literally, it doesn't matter how high you go. The answer is absolutely always a constant 2. No way, right? It feels a bit like a magic trick for sure, but it's just pure algebra doing its thing behind the scenes. Any 3 consecutive numbers can be represented algebraically as n minus 1, n, and n plus 1. If we take their squares, add the first and the last, and subtract twice the middle, we get this beautiful algebraic cancellation that reliably spits out the number 2 every single time. It's an algebraic identity operating perfectly right there in the background. Moving on to Section 2, Visualizing Algebraic Identities. Now, instead of just rote memorizing the letters for a minus b squared, let's actually look at the geometry here. If we start with a large square that has side lengths of a, the total area is a squared. We then split that side length a into 2 segments. One is b, and the remaining part is a minus b. The gray square in the top left represents our target, the actual area of a minus b squared. Let's break this down to prove the identity visually. To isolate that small gray square of a minus b squared, we take the big area, a squared, and we just subtract away the extra pieces. The red rectangle has an area of ab. The yellow rectangle also relates to ab but has a slight overlap. When we carefully subtract the geometric areas from the large square and adjust for the parts we subtracted twice, we are left with the exact algebraic identity, a squared minus 2ab plus b squared. The geometry perfectly matches the algebra. It's like a giant puzzle. All right, so what happens when we add a third variable into the mix? Here is the identity for a plus b plus c squared. Instead of dividing our square into 2 sections, we divide the side length into 3, a, b, and c. When we multiply the sides to get the area, the giant square divides beautifully into 9 smaller shapes. We get 3 squares right on the diagonal, a squared, b squared, and c squared, and then we get 3 pairs of matching rectangles, 2 ABs, 2 BCs, and 2 CAs. We literally just add the physical areas together to get the full expanded formula. Okay, but what if we jump into 3D? This is a plus b cubed. Instead of a flat area, we are calculating the volume of a giant cube. A large cube with an edge length of a plus b structurally breaks apart into exactly 8 pieces. We get 1 large cube of volume a cubed, 1 small cube of volume b cubed, plus 3 flat cuboids of area a squared b, and 3 tall cuboids of area ab squared. Add up all the 3D blocks, and we have physically built the formula, a cubed plus 3a squared b plus 3ab squared plus b cubed. Section 3, Factoring with algebra tiles. Now, what's really interesting here is how we can turn factoring into a literal tactile puzzle. Let's multiply 2x plus 3 by 3x plus 1. We represent the top using 2 x-length tiles and 3 unit tiles. On the side, we lay out 3 x tiles and 1 unit tile. When we fill in the rectangle they create, the puzzle pieces perfectly snap together. We get 6 large yellow x squared tiles, we get 11 blue x tiles in total, and we get exactly 3 red unit tiles. You just read the grid, and boom, we have our expanded polynomial, 6x squared plus 11x plus 3. Section 4, Master List of Identities.
All right, now that we've grounded this visually, here is our master toolkit. We have 11 core identities. Notice the absolutely crucial difference of squares. X squared minus y squared. Geometrically, just imagine starting with a large square, cutting a smaller square out of the corner, and rearranging that leftover L shape into a perfect rectangle of x plus y times x minus y. Also, let's step through the sum and difference of cubes. If we actually expand x minus y multiplied by x squared plus xy plus y squared step by step, the middle terms, like positive x squared y and negative x squared y, they just beautifully cancel each other out, leaving us with exactly x cubed minus y cubed. And the exact same beautiful cancellation happens for x plus y multiplied by x squared minus xy plus y squared, leaving us with x cubed plus y cubed.
Section 5. Applying identities to problems. Identities are a real game changer because they turn tedious arithmetic into simple mental math. Imagine trying to calculate 43 squared in your head. Pretty difficult, right? But if we view it as 40 plus 3 squared, we just use the identity. 40 squared is 1600. 3 squared is 9. 2 times 40 times 3 is 240. Add them up, 1849. Same with 29 squared. Treat it as 30 minus 1 squared. Or look at 55 squared. Just visualize it as 50 plus 5 squared. 50 squared is 2500, 5 squared is 25, and 2 times 50 times 5 is 500. So 2500 plus 500 plus 25 instantly gives us 3025.
Okay, let's tackle a beast of a polynomial. If we see an intimidating string like 9a squared plus b squared plus 4c squared minus 6ab plus 12ac minus 4bc, don't panic. Just look for the geometric patterns. Step 1. Identify the base squares. 9a squared is clearly the square of 3a. B squared is the square of b, or negative b. 4c squared is the square of 2c. Because we have negative signs on the terms containing b, we can lock in a negative b. Match up the middle terms, and we realize this giant equation is just a beautifully wrapped up square of 3 terms. The whole shebang instantly collapses down to 3a minus b plus 2c squared. So the crucial point is that recognizing these identities saves massive amounts of time. Consider this debate from the text between two students. They want to multiply a minus b squared by a plus b. James does it the hard way, expanding the square into 3 terms and multiplying them out. But Rashma is clever. She breaks apart the square into a minus b times a minus b. Then she pairs one a minus b with the a plus b to instantly trigger the difference of squares identity, giving her a squared minus b squared. Rashma's path is incredibly elegant and, frankly, way less prone to simple errors. Let's push this to the limit with a multi-step proof. We are given that a plus b plus c equals 5 and ab plus bc plus ca equals 10. We need to find the value of that massive a cubed plus b cubed identity. First, we use our squaring identity. Since 5 squared is 25, we know a squared plus b squared plus c squared plus 2 times 10 equals 25. That means our a squared plus b squared plus c squared portion must equal exactly 5. Now plug that right into our long master identity equation. We take the sum, which is 5, multiply it by our squares minus our pairs, so 5 minus 10, which is negative 5. 5 times negative 5 leaves us with a neat, clean answer of negative 25. It bows right to our structured logic.
Section 6. Viewer quiz and practice. Here is a really thought-provoking question, directly from the Think and Reflect section of our source text. We know that a plus b squared expands to a squared plus 2ab plus b squared. So under what exact conditions would a plus b squared be perfectly equal to just a squared plus b squared? What has to happen to that middle 2ab term? Think about what values of a or b would make that middle piece vanish entirely. And here's a parting puzzle for you to practice. Look at the expression n cubed minus n. If we factor out the n, what are we left with? And how can we use our master identities to factor it down further into 3 distinct linear terms? Once you see those 3 terms side by side, ask yourself, why must multiplying those specific 3 numbers together always result in a multiple of 6? It's a gorgeous piece of logic once you unlock the structure. By seeing the squares, cubes, and rectangles hidden inside the equations, we shift from memorizing blind rules to understanding the very foundation of mathematics. I want to leave you with this thought. How does visualizing equations change the way you look at everyday math? The next time you see a complicated formula, I hope you don't just see letters. I hope you grab a piece of paper and start sketching out the geometry. Thank you so much for joining me on this explainer, and keep looking for those hidden structures everywhere.